Okay, so in tutorial 3, let us see how many questions we have. So can you see tutorial 3 questions?
Yes, sir.
Yes, sir.
So we have altogether 5 problems. So these problems are based on lecture 3 materials. So the first question is based on the reliability and risk. Second question is estimation of 100-year and 50-year flood using normal distribution. Third question is plotting position and non-parametric distribution. And fourth question is LP3 distribution. And question 5 is really to compare the flood quantiles or the design floods we are estimating based on 50-year and 100-year return periods, and to comment on any differences between the methods. So we have the data given for some of the problems, I think from problem 2 to remaining problems. So this is for every year. We have the annual maximum flow data. So that means that in 1975, the highest flow was 9840 meter per second at this location. And we have data up to 2014 for these catchments, and we have the standard normal distribution table there. And we have also the LP3 distribution and its table for the frequency factors as well there. So these are the problems there. So let us start with our question 1. So question 1 is telling that a temporary coffer dam is being designed to protect a 5-year construction project from the 25-year flood. So the coffer dam is the temporary structure that we built during the construction of an important project. For example, if we are building a barrage or dam or bridge or something, then we create a dam or embankment around the project site so that during the construction of the project, a big flood does not come and destroy the site. So in this case, we have to find out what is the probability that the coffer dam will be overtopped at least once during the 5-year project time. That is the risk. And then the reliability. If we can find the risk, then we can find reliability as well. So basically in this question, we have to use the risk equation that I introduced in the lecture. So let me go to Excel, which will be better. So I'll stop share this one and then I'll go to the Excel sheet. Okay, so in this problem, we can see that the temporary coffer dam to be designed to protect a 5-year construction project. So the life of the project is 5 years. So So life of the project. Which is N equal 5 years. And the return period that we have to consider in the design is 25 years. So T equals 25 years. So we know from our lecture that risk is defined by, in terms of probability of exceedance, risk equals 1 minus 1 over T and to the power of N. So that is the risk. So we can estimate this by this way, that we can write the equation that equals 1 minus the bracket 1 minus 1 over T, which is 1 divided by T is our return period 25 here. So I'm selecting that cell. And then to the power of that of N is 5 years. So the risk is 0.1846. So in terms of percentage, the risk is 100. So there is 18%, 18.46% risk that at least once during the 5-year period, the coffer dam will be flooded. So do you think it's a high risk or low risk? So do you think it's a high risk or low risk? 18% risk.
Low risk, Prof.
I think it's a high risk because 18% is quite high. So almost 1 in 5 times risk, which is 18%, which is quite high risk in my opinion. Because when you design this kind of infrastructure, then huge cost is involved. And if the flooding happens, then it's a kind of a big problem because there will be a lot of losses that you have incurred during the construction. So the return period that we have considered, 25 years, may not be adequate. So if you want to reduce the risk, then we have to consider a higher return period flood to design the temporary coffer dam. So for example, if you consider T equal 50 years here, then you will see that our risk is becoming 9%. So there is 10% risk there. So if you consider it 100-year flow, then your risk will be 4.9%, for example. So you see your risk is not that much increasing, like reducing from 50 year to 100 year. So if it is an important infrastructure you are designing and you are building huge cost, then we have to increase this return period, return level, so that risk is very low. So if you consider 1,000 years return period, then your risk is becoming 0.5% in a year. So really, you have to consider the risk, which depends on the type of the structure that you are building.
Excuse me, sir?
Yeah.
What does return period mean again? Like, why is it bigger, better?
A return period higher means that we are considering a big flood in the design. That means that your embankment has to be higher, so that when the flood is coming, the flood cannot enter into your side. So higher return period means that say 100-year return period. 100-year return period means that a flood that will come on average 1 in 100 years time. Now, if I consider a 50-year flood, then 50-year flood discharge will be smaller than 100-year flood, because that will come 1 in 50 years time. The return period is the average time between the successive occurrence of the events over a long period of time. Is it clear to some extent?
Yeah, thank you.
Okay, return period. That is return period. Sometimes we call it average recurrence interval as well, ARI, or average recurrence interval as well. Same thing. So in this problem, our return period was 25 years. So let us go back to 25 years. And then if we have the risk, and reliability is 1 minus risk basically. So reliability is reliability is 1 minus the risk. So that is the reliability, and this is the risk here. Okay, so that is the first question we have done. So any question on any issue on this question? I think it's quite simple application of the equation basically. Okay, so let us go to the question 2 now. So in question 2, we'll be using a normal distribution. So annual maximum flood data for the Cypress Creek for the period 1975 to 2014 are listed in table 1 in your tutorial problem. Assume that the Cypress Creek data are normally distributed. Find the peak flow for 100-year flood and 50-year flood. We want to find out basically Q50, and we want to find out Q100 equals how much. And also we want to find out Q50, how much for this data. And the second one is the return period that a flood will be less than or equal to 2000 CFS, cubic feet per second, like that's the American unit, it doesn't matter. So basically when you want to find out this kind of problem with the normal distribution or any kind of distribution, we generally deal with CDF, cumulative distribution function. So CDF is written by F. So F for Q100. So F for Q100. So F is defined by 1 minus 1 by T. So F is defined by 1 minus 1 over T. So for F for Q100 is basically 1 minus 1 over 100. So our F is 0.99. So we have to find out for this, we have to find out the Z value, because our equation to find the Q is this equation here. So to find out the for any value of X with certain probability, we have to find X equals mean plus Z value, with the standardized normal variate, and sigma is the standard deviation. So basically, our equation would be x equals mean plus standard deviation times z. So we can find out the mean of the data and standard deviation of the data by basically by using Excel. So let me find the data, and then we can find out it from the mean and standard deviation. So data should be somewhere here. So this is our data. Can you see the shade here?
Yes.
So this is our data here, that the ER and flow data. So this two column is the data. So in the equation, we have to find out the mean and standard deviation of the data. So basically, we can copy this data and go to that our sheet there. So I go a little bit down here, and then let us copy the data. So I think I have to go to the first cell here. So this is our data. So we have to find our equation was that Q T, so or X equals mean plus standard deviation times Z value is the normal variate. So it's normal distribution. That's why you have to use Z. Okay, so the average we can find out easily from here. VERAGE, average of the data. So we just use the equation and then select the data. So that is our mean. And then standard deviation of the data will be equals STDV of the data. So that is our standard deviation of the data. So this unit will be in meter cube per second, both of them. This unit is in meter cube per second. This is also in meter cube per second. Okay, so what would be the, so we found mean and standard deviation. Now we have to find the Z value. So we found that our F value for Q100 was how much? It was 1 minus 1 over 100. That is our F value. So for this F value, for 0.99, we have to find out the Z value. So we can find that in from the table of the normal distribution. So then let us go to the table of the normal distribution that I want to find out F value for 0.99, positive 0.99 Z. So let us go to the normal distribution. Okay, so this is the normal distribution table. So these are the F values entered into the cells here. So for to find the F, when F is 0.99, what is the Z value? So we have to see where is 0.99 happening here in this table. So we can see that 0.99 is really happening somewhere here, 0.9898 and 0.9901 somewhere here. So it means that our Z value for 0.99 will be close to 2.3, and the reading of this cell is here. It will be close to 2.33, but little bit smaller because for that value we have 0.9901. So it is in between these two. So we have to do an interpolation. So for F value of 0.9898, we have our Z value 2.32 at this cell. Our Z value is 2.32. And at this point here, for F value of 0.9901, our Z value is 2.33. So we have to do an interpolation between these two to find out what is the F value for 0.99. And I'm sure you can do the interpolation. So once you have done the interpolation, then we can find out the F equals 0.99. So any issue with this diagram? We use this table. So you see, these are the Z values, and these are the F values in the cells. And most of the time, for a particular F value, to find the Z, we have to do the interpolation, because most of the time you see it does not exactly match the value given here. So basically, in doing the interpolation, I have done the interpolation here for you in the solution here, that for F is this Z, like there are two Z values given for given F value. So the difference between the Z values divided by the difference of this F, and then multiplied by the difference from 0.9901 minus 0.99. So the difference is becoming this. And then really we have to subtract this difference from 2.33, and the Z value will be this. So any question, any problem with this? So by interpolation, we are getting the Z value 2.32667 by this interpolation. But we can use the Excel function as well. So to use it from Excel, we have to use the function called NORM INV, and that the first term of that would be the probability that we are looking for, which is 0.99 or F value, and the limit of the probability is 0 to 1. So that is the equation we have to use to find our Z value close to F90. So Z value, which is corresponding to 0.99 of the cumulative probability CDFF, equals NORMINV, and then we have to write down whatever Z value, whatever F value we are looking for, and 0 and 1, they are parameters that really we have to consider. So that is the Z value we are coming from Excel function is 2.326, and from interpolation we got very close to that as well.
Wait,
So is
so
that clear?
can you explain the formula again with the numbers, the three numbers, 0.99, 0, and
So
1?
the norm in, and this is the F value that we are looking for. And F value is coming from that return period, is that right?
Yep.
And then your 0 and 1 is the limit of the probability, 0 and 1. You cannot go beyond it because it's a standard normal distribution.
Oh, okay, yep. Gotcha.
So once you got that Z value, then we can find out our 100-year flow estimation easily from our data that we are using. So we got the Z value as so what is the Z value we got?
2.32667.
2.326.
6.
In fact, we can do it from here directly here with the NORM INV and then 0.990 to 1, the limit of the scale. So that is our Z value. So basically now we can find out our Q100, which is our X here, that is equal to our mean, which is here, plus our standard deviation is here, times our Z is here. So Q100 is 10952.7. So how we can find out Q50 now? Q50. So to find the Q50, first we have to find what is? We have to find F value, is that right?
F value.
The first F value is 1 minus 1 over 50,
50.
which is 0.98. So now we can find out our Z value. So our Z would be NORMINV 0.98021. So our Z value is becoming 2.05372. So then we can find out our Q50, which is equal to mean and standard deviation, like the mean plus standard deviation times the Z, we have got it here. So that is our Q50. So that is our Q100 flow, and that is our Q50 flow. So is this clear to everyone?
Yes, sir.
Clear to everyone else as well?
Yes, sir.
Yes, sir.
Okay, that's good. So next part is that, or next part of the question is that we have to find out for a given flow, we have to find out that probability of exceedance of that flow. So let us see that problem. So that is there. So so for C, we have to find out the probability that a flood will be less than or equal to 2000 meter cube per second. We have to find out the probability. Now we know the flow, we have to find the probability of that flow. So our X is given here. So if X is given here and we know the mean and standard deviation of the data, then we can find out the Z, is that right? So what is the equation to find out Z equals X minus mean divided by standard deviation. So that is the equation for Z. So in this case here, we know the X is given 2000. We can find the Z. So Z would be our mean. So not mean, our X value, which is our 2000 minus mean of the data is this divided by the standard deviation of the data here. So Z value in this case is minus 0.7207. So it's coming to the left side of the standard normal distribution. So for that Z, we have to find out equivalent F value. Again, we have to go back to the table and we have to interpolate for the F value this time. So that is all right, we can do it, but we can do from normal distribution, which is we can use the this formula equation, this formula now. That now we have to use the function norm dist. So this formula is NORM norm DIST, norm distribution. And we have to write that Z value that we are looking for, we are interested, which is our 0.7207 and our scale is 0 to 1, and this is our argument of the equation TRUE. This is the way that Excel has written the function. So we have to use the true here because this is the form of the function. So once we say norm dist like this for any Z value, then we will get that F value, equivalent F value. So this is the equivalent or F value corresponding to that. So once we know the F value, then we can find out our T value because we know F equals 1 minus 1 over T. That means that we can find out our, so 1 over T will be, 1 by T will be 1 minus F, so equals 1 minus F is, got it here. So that is our 1 over T, so our T would be inverse of that. So 1 over this value here, which is T equal 1.308 here. So that is the return period for 2000 meter cube per second flow.
Yes, excuse me, sir.
Yeah.
The value F up there, what's the formula you use to get the F?
F equals 1 minus 1 over T.
Sorry, up there, go up. That value, no, up one, up
So
more.
that is the, we are trying to find out
No, the other one.
like for a particular Z.
No, sir. The one when Z is 0.72, F equal Move your cursor up,
Up here.
up. Yeah, that one. What's the formula for that?
When Z is 0.720, what is F?
Yeah.
That is the interpolation. We are doing the interpolation in this way.
So what formula do you get?
So interpolation is like we are using a table. You know the table I shown you previously?
Yeah.
That
But
is
your
one way of doing it. But if you are using Excel directly, then you don't need to do that way. Rather, you use this function.
no, I'm just asking for your formula. Like the formula you use?
Yeah.
Yeah, pressing it. Yeah, that one. Can you explain the formula you use?
This is a interpolation problem because we are trying to find out if Z is for Z this, F is this, for Z this, F is this. So if the Z is in between, what is the F value? So in this type of interpolation, what we do, we find the difference here. So difference of 139 minus the difference of these two cells on the top, divided by the difference of these two cells in the bottom. And then times the difference of any of the reference cell, which is basically, if I am taking this on reference, so this minus that. This is interpolation. It's a solution of the two similar triangles.
Yeah, got that.
Yeah. So this is the interpolation issue from the geometrical issue that if you have two similar triangles, how it's solve it. Okay, any question on this?
Yes, sir.
Yes.
Sir, can you hear me?
Yes, I can hear you.
Oh, yeah. In an exam situation, would we be required to do it in like in the interpolation form or in the Excel form?
I think Excel form is not better. Why you do, if it's open book exam,
Okay.
then you do the Excel form.
All right then.
Interpolation is good when you are closed book exam. When you closed book exam, then you are not allowed to use your computer. So that scenario, you have to use interpolation. But here, you must use the Excel. Which is this
So
equation here.
what's the formula for interpolation for a negative number?
Interpolation is really,
Like for
you know,
Excel,
like it's
the
a
formula.
very simple thing. Really, interpolation is
Yeah, I know
like-
how to work out the interpolation, but how would I type it into Excel to get the value
so.
quickly?
Can you see this cell here?
Yeah, I know how to do that.
Okay, so that's the interpolation way of doing it.
Yep, I want to do it quickly through Excel. So what formulas do I type in?
So this is the formula I have typed. So this is the difference between these two cells on the top,
Yeah.
divided by the difference between these two cells on the bottom.
Isn't there like a shortcut command to get it?
No,
get the
there is
value?
no shortcut command for interpolation. Unfortunately.
How come up there is the other shortcut command for it? How come this one it doesn't have?
Because interpolation Excel thinks that everybody can do it, and really they have not given any
No, can you scroll up? Sir?
particular
Scroll up.
function for interpolation.
Scroll up your page.
Sorry?
Scroll up your page. Scroll up like scroll up more. Yeah, that function right there. The green one, norm
Yeah.
INV.
Yeah.
Yep, that one. You can use that to get the value. How come this one you can't?
You can get that
Oh,
one to
wait.
get the Z value or F value.
Oh, my bad. Never mind. Yep, it's all good, sir. Thank you.
It is included in the coming quiz next week.
When you are using the table, then you have to use interpolation. But when you are using Excel, then you can use the Excel function directly to get the Z value or F value directly from there.
Oh,
No,
so
I-
F, there's no formula for F. There's no shortcut for F, but there's a shortcut for Z. Is that what you're saying, sir?
So there are two things here. There are two functions that we are using. One is the like there are two functions that we have introduced. One is the norm inf, another is the norm dist. There we are using two functions here.
Yep. So what's a norm dist used for? The second one, what is it used for?
Okay, let us see.
So for norm INV is used to find Z. What about norm dist?
So norm dist is using, we are using the norm dist for any probability given 0.99, that is the F value, okay? So F value given, and we are trying to find the Z, which is the standard normal variate. Is it clear?
So to find Z, you use that one. What about
That
to
one.
find
And the
F?
other one,
Yep, now you're missing F. So how do you find F?
so for this one, we have the Z value and we are trying to find F. So this is the Z value here, you see? And how you find the Z? Z equals the given flow X minus mean divided by standard deviation of the data. That is the equation to find the Z. And once you know the Z, then to find the probability of F, we use this equation. You see, Z is written here. Okay, I think I have spent too much time on one problem. Okay, so let us go to now question 3 quickly. So question 3 is we have to use Coulom's plotting position formula to obtain the return period of the annual maximum flood data shown in table 3.1. So this is the data given. So I am going to create another new sheet, sheet 4, and I'm copying this data here. So in Coulom's plotting position formula, what we do is we sort the data. So these are the original data. So this is a non-parametric method. So we go to data and then we sort it according to our, sort the data from as per our flow, highest to largest to smallest, okay? We have sorted the data, flow data according to the highest, the top, second highest later on, and so on. And then we rank the data, rank M. The highest data is given rank 1, and the second one is given, sorry, rank 2, and so on. So now,
Sorry, can you show us how to sort it again? Just quickly.
how to sort the data?
Yeah.
Sorting of data is very simple because you select the data, you have to select both the column, and then go to the data, and then go to the sort. And then we are sorting our flow, which is our okay. So I think we have to select this data here because I see there is a blank cell on the top, which is not right. So now go to the sort and then sort by our flow and largest to smallest. Okay, can you see it? Everybody see
Yep,
it, how to
got
sort
it,
the
got
data?
it. Thank you.
And if we say okay, then it will sort it. And then we put the rank. Rank M equals 1, 2, and so on. So I copy it down up to the full my data. So our N is 40. Our M, like our M is 1, 2, 3, 4, and our N value is 40. There are 40 data points here. N is 40 because we can see on the top there are 40 data points here. Now our return period T is estimated by the formula given here according to Coonan's plotting position is N plus 0.2. So N is our 40 plus 0.2, which is given in the equation, divided by rank. Rank is our, in this cell, our L3 rank minus 0.4, which is constant. So this is our T, return period. For the highest flow, return period is 67 years. And if we copy it down now, then we'll get the return period for all the flow in years. So that is our return period T for each of the flow. So now in non-parametric method, we have to plot this return period in x-axis and flow on the y-axis. So that's why I'm copying it here. So I'm copying it here again, Control V here. So now I want to do a plot of these two. So I'm selecting the data and then I'm going to do a plot, insert, and then come here and we can do a scatter plot like this. So that is the plot of the data, and we can add the axis title. So our x-axis title is our return period T. T in years. And our y-axis title is our discharge in meter cube per second, in meter cube per second, cubic. So, but you see, one problem with this data is that this looks very like it's not a straight line. So what you can do to make it a straight line, we can format the axis and select the logarithmic scale. So we can select the logarithmic scale here, and then you will find say more linear kind of line. Okay, so now we can fit a regression line here. Generally, we have to draw a line by the best fit line, but in regression, but we can do some regression like this. We can select the data and then we can add a trend line in the data, and we select linear here, and then we say the display equation of the chart, display R square of the chart. So once we do that, we'll find that there's an equation here, which is a kind of, you see that like this is the problem when you do the linear fitting of the data, and really it does not work very well there. So if we remove our log scale from there, format axis, and I remove the log, and you see like the line, it looks like this. So this is the problem with the non-parametric method, that really you have to draw a line by hand, generally to make a best fit of kind of thing, but it's not easy to make an equation for that. But anyway, once you have this equation, then we can estimate our flow for Q50 and Q100. So Q50 would be from according to this equation that our intercept is 2920. So 2920 plus 227.75 times X is our 50 years. So that is our Q50 estimation according to non-parametric method. If we assume that the fitted line like that, Q100 would be, again, our intercept is 2920 plus 227.75 times X is 100, return period is 100. So our Q100 estimation is meter cube.
Oh, excuse me, sir. How do you show the formula inside the graph? How do you show the formula? Because I created a trend line, but there's no formula included.
So you have to, when you do that in Excel, then you have to, there is an option in the bottom that you have to tell that display equation in the chart and R square in the chart. Go down and then there is an option.
Okay, yeah, I got it. Thanks.
Okay, so any question on this?
Yeah, I have one. The trend line, it has to be linear or can be the best fitting one?
It should be best fitting line. So that's why when we use the non-parametric method, then really the best thing would be that you draw a line, best fit by your hand. And then for a given return period, you read from the graph.
But we have that in a trending line, also logarithmic one, and in that case, that one wouldn't fit better.
So yeah, there are many different ways that you can set the equations. For example, if you go logarithmic scale, let us see. So if you do the logarithm upon, and you got, okay, so you got, now you got this line, is that right?
Yeah.
So with the logarithmic scale, you get better fit.
Yeah, and the R square is like 0.9 something in that case.
So let us do that on. So so delete this line. So okay, so let us do that logarithmic setting and let us see what is the difference in our estimation.
Okay.
So at trend line, and this time we want to do logarithmic because it's a logarithmic shape of the curve. And then we want to see the equation on the chart and R square value on the chart. So we are finding that our R square is quite good. Is that right? And our equation is in this form. So now let us use this equation and see what is the value of Q50 and Q100, okay? So let us do Q50 according to this equation. It will be 1130.6, which is our intercept of the model, and then plus 3039 0.3 times ln of the return period, which is 50 years in first case. So we are getting 13,020 meter cube per second for Q50 and Q100. Three 39.3 times ln of 100-year return period. So you can see here that the difference between these two estimation, particularly for 100-year, is quite high. So if we ask to make some comment on it, that between the two different fitting, that for higher return period, this is going to underestimate because the line has been dictated by the smaller points too much. And this line is going this way. So higher quantized, you see Q100 in the second case is becoming 15,000. And in the previous linear case is 25,000. But nevertheless, linear fit is quite poor because R square is very low. So basically, between these two, that would be more reasonable estimation for parametric approach.
Can we like combine two, like for example, the lower number do as a logarithmic and then see if the linear equation is more better for the higher number in that case?
This is not recommended because this kind of flow data, they have a lot of error in it. So generally, we don't rely on the data too much because it's a sample of a big population. And also there are a lot of measurements errors in this data.
So sir, what would you recommend in that situation? Which for us is the best fitting, the linear or the logarithmic in that case?
In this particular case, the logarithmic fitting is better, giving better R square. So in terms of the equation, that is the better form. But when we do the non-parametric like this, we draw the curve by hand and we really interpolate by the table. For example, if I have to draw the curve, this I put this line along that way. I'll put up.
Okay, thank you very much.
And then for 100-year or for 50-year, I'll be able to plot it from here. But problem with the 100-year is that the highest data point has a return period of only in between 60 to 70 years. So we have to do a lot of extrapolation of the curve. So the 100-year has a lot of error due to the extrapolation error. So for higher flow estimation, this kind of approach is not good. It is good when you are on to estimate 10-year, 20-year, 30-year flow, then it's quite reasonable. But if you want to estimate higher flow over 50 years, like 100-year flow or 500-year flow, then it will be quite problematic. So basically, that's why we have to use a number of different approaches. And in the design, we have to consider we have to use our hydrological knowledge and judgment and experience that which one we should recommend for practical design. Okay, anyway, so that is our non-parametric method. So basically, to summarize it, what I did was I ranked the data with the highest data point in the rank 1 and second highest rank 2. And then I estimated the return period by this plotting position formula. There are a number of formulas given in the lecture notes. And then I created a plot between these two, scatter plot. And then I produced a scatter map, scatter plot, and then I fitted a linear regression line, either linear or non-linear, There are different fittings in Excel, you see, in build. And from there, we can estimate our Q50, Q100 based on the equations. Any question on this? So it's clear to everyone, is that right?
Yes, sir.
Okay, good. So let us take the attendance and then I'll go to the next question, which is very important, with the LP3 distribution log, Pearson type 3 distribution. So Dr. Saika, can you take the attendance? Is Saika here?
Prof, I'm here. Okay, I'm taking
If you
attendance.
can take the attendance of the student, that would be good.
Yep, I can do. Okay, everybody. Good afternoon. I'm now taking your attendance. Please be attentive and response. Okay. Ali Muhammad Ahmedi.
Yeah, I'm here.
Thank you. And Daniel Al-Saifi.
Yes, I'm here.
Thank you. Ahmed Sharmad.
Yes, I'm here.
Thank you. Ayman.
Yes, I'm here.
Thank you. Susan Amaksashta.
Yes, I'm here.
Thank you. Asif Muhammad Asifullah.
Present.
Thank you. Sinan Sarmad Yusuf.
Yep. Here.
Thank you. Alexander Leonardo.
Yeah, I'm here.
Okay, thank you. Kapak Bestrin.
Yes, here.
Thank you. Alex Brook.
Yep, here, miss.
Thank you. John Klimquin.
Yeah, here, miss.
Thank you. James William.
Here, miss.
Thank you. Salah Darwick.
Yep, here. Yep.
Thank you. Okay, Desha.
Here.
Thank you. Nauruz Dhangana.
Yes, miss.
Thank you. Suleiman Faisal. Suleiman Faisal. Suleiman Faisal. All right. Oliver Frame.
Yeah, I'm here, miss.
Thank you. Hanifa Darjestani.
Yes.
Thank you.
Can you hear me?
Yep, I can hear you. Thank you.
Can you hear me? You called my name?
Hanifa.
Yes.
Yep.
Did you
Bikal
mark my-
Gimeri.
Okay.
Bikal Gimeri. That's right. Laslan Vincent Gibbons. Laslan Vincent Gibbons. Gibbons. All right. Gursabijit Singh.
Yes, miss, I'm here.
Thank you. Kashim Hassan. Kashim Hassan. Kashim Hassan. Okay. Daniel Atinso.
I'm here.
Thank you. Biha Jamshed.
I'm here.
Thank you. Benjamin Stewart.
Yeah, I'm here, thanks.
Thank you. Azim Khan. Azim Khan. Okay. Grismi Kanal.
Yes, ma'am. Yes, ma'am. I'm here.
Okay, thank you. Manali.
Yes, miss.
Thank you. Agatha Koniska.
Here.
Thank you. Asin Lalinda.
I'm here, miss.
Thank you. Ju Feng Luo.
Yes, miss.
Thank you. Vitraj Mitra.
Present, miss.
Thank you. Arun David.
Yep, I'm here.
Thank you. Ayush Mishra.
Yep, present.
Thank you. Abhinav Nashra. Abhinav Nasrallah.
Yeah, here.
Thank you. Neil Rakesh.
Yep, present.
Thank you. Rohan Anthony.
Present.
Thank you. Austin Ivan.
Yeah, I'm here.
Anushwa. Anushwa.
Is that Anushya Pravindan?
Yep.
Yes, miss.
Okay. Thank you. Morshid Nim.
Yes, miss, here.
Thank you. Muhammad Ali Raja.
Yes, miss.
Thank you. Yusuf Hashim Hisham. Yusuf Hisham. Yusuf Hisham Rifat. Okay. Violetas Dennis Devin Rodrigo.
Present, miss.
Thank you. Jacob Rodriguez. Jacob Rodriguez. All right. Brandon Roses.
Yep. Here,
Thank
miss.
you. Ozi Sadi. Wazi Sadi.
Yeah, here.
Thank you. Mohammed Sadiq.
Yeah, I'm here.
Right. Thank you. Sabita.
Yeah, I'm here.
Thank you. Vinabu Sreshta.
Here, miss. Thank you.
Thank you. Anilban Singh.
Yeah, here.
Thank you. Mutasam Tai.
Yep, I'm here.
Thank you. Norris Nadir Kaushal.
Yes, miss.
Thank you.
Miss, can you just call me now Stomina? It's too long.
Tamena. Oh, all right. No worries.
Thank you so much.
Actually, I'm a bit confused. Whose name usually you used to as a nickname?
I know.
Because some are family name here, so they are
Yeah.
usually in the paper. But
Thank
it's
you.
okay.
That's
Okay.
fine.
Okay. Minhat Tran.
Yes, miss, I'm here.
Thank you. Daojiang Wang.
I'm here.
Thank you. Jijiang Zhang. Jijiang Zhang.
Yeah, I'm here.
Thank you. Mara Kohilo.
Here, miss. Here.
Thank you. Ali Ahmad.
Yes, miss, I'm here.
Thank you. Nilufa Afrin.
Yes, ma'am, I'm here. Thank you.
Thank you. Abu Huraira.
Yes, ma'am. Abu Huraira here.
Thank you. Thank you all. That's all.
Okay, it's done.
Yep, Prof, I'm done.
Okay, thanks, Dr.
Sorry,
Saika.
sir.
So-
Sorry, sir. Before you go, you have to upload the lectures and tutorials of previous weeks and because of videos because you have not uploaded them. And can you also upload the solutions for the tutorials because we need them for the exams next week. And we've been trying to study, but you haven't uploaded any
So
content.
solutions are not there in the tutorial.
No, sir. So you need to
Solutions
upload the
should-
videos.
Solution should
for-
be there.
No, sir.
I'll check.
No solution. No solution.
Yes, sir, because most of the time we are not able to be here, so it's better if we can watch the videos.
Yes, we need lecture 3 and
All the
tutorial one.
tutorials.
The
We
second
need
one and the
tutorial
third one.
solution.
So second tutorial solution not in the views.
No.
No.
No, sir. Can you just upload all the videos that you've recorded? So any video of any lecture of any tutorial from the previous weeks, can you just upload all of them, please? And can
Yeah.
you do that today, sir? Because we should all want to try to study, but none of us have access to anything. So none of us can study. We emailed you as well, but I don't know if you saw the email.
Okay, so I'll do it by tonight.
Yes,
Oh,
sir.
thank you.
Please. Thank you. And make sure
So-
everything's up there. So like solutions.
I think
for
one
everything.
student was asking that how we estimated the T. So to estimate the T, this is the equation that we use. This is the Kunan's plotting position formula. So our n is the number of data points 40, and the m here is the rank of the data, which is the highest data has the rank of 1, 2, 3, and so on. Okay, so let us now go to our question 4, which is we have to use the LP3 distribution, log Pearson type 3 distribution for the data.
Excuse me, sir. Just before you go, I'm here as well. I think so. Like I just didn't have my name on the list.
Can you, Dr. Saika, Dr. Amir is here. Our PhD student Amir is here. So if you can include his name, he's I think coming from today.
Including his name here.
Excuse me, sir. Sir, my name as well. Urpita.
Urpita.
So Urpita is coming as well. So put Urpita's name as well.
I'm adding you there.
Thank you.
Okay, so now we'll be using LP3 distribution. So LP3 distribution is very important. Okay, so this is the flow data given for the site, and we have to use LP3 distribution. So LP3 distribution, if you want to use LP3 distribution, then the equation is in this form, that log 10 of QT equals m, which is the mean of the log data, and then standard deviation of the log data times a frequency factor, that is KT. So in this equation, m equals mean of the log data, mean of log Q, and S is the standard deviation of log Q, and KT is the frequency factor. This frequency factor for LP3 distribution, which we have to obtain from LP3 distribution table. So the first step with LP3 distribution is that we estimate the log of that data. So we estimate log of Q, which is log of 10 times, I think we don't need times here, log 10 of the this value here. So that is our log data here. And then we have to find the mean of that data, which is our m. So basically our m would be average of these data values here. So that is our m. And what is our s? Equals STDV of this data here. So this is our m and s. We got it from for these equations, and we have to find out KT for our 50 year and 100 year. We have to find out KT for 100 year and 50 year. So we have to find out K50 basically, if you want to estimate a 50-year flow. So K50 is a function of the skewness and the T value. So T is 50, and so we have to find out the skewness of the data as well. So let us find the skew. Skewness of the data is SKEW of the data. So skew is minus 1.21022. So for this skew, we have to find out. So write down this skew in your book, 1.21022. So that is the skew of the data. So we have to find out our K frequency factor for 50 year and frequency factor for 100 year for this skew. So can you write down this skew value in your book, because I am going to another sheet now with the table for LP3 distribution. So I'm going to another table. So I'll share the screen, this one now. Okay, so you can see now that this is the, in the problem sheet, it is in the last pages, that this is the frequency factor, KT value for different return period. So for 50-year return period, which is this year 50-year return period, and what is the skew value? What is our skew coefficient?
Minus 1.21022.
So we have to find out the skew minus. So we have to go to the next page, which this is the for plus skew and this is the minus skew. So our skew coefficient minus 1.21022. So minus 1.21. So it is this is the skew for minus 0.12. And this is the skew minus 1.3. So minus 1.2 and minus 1.3. So minus 1.21 is in between. So we have to go along, and for 50-year return period. So this is percent, 50-year means 2%. You see 50-year here, and which is equivalent to 2%. So 1.21 is 1.379. So write it down that for skewness of minus 1.2, your KT is 1 point. So this is the for minus 1.2 skew for 50-year return period, our KT is 1.379. 1.379. And for skew of minus 1.3, our KT is 1.324. So by interpolation, we have to find out the for skew of minus 1.21022, what is our KT value? So this is an interpolation problem. So that is for the 50 year, and now for 100 year. For 100 year, we have to use these values. We have to use 1.449, 1.449, and 1.383. So is this clear from the table?
Yes, sir.
Anybody has any confusion with this? Any question? So if there is no question, I assume that it's clear to everyone, because I am taking the skewness data of the data, log data, and the return period from here. And then I am finding the corresponding values. So basically, our skewness should be close to 1.379 because our data is 1.2. So the for 50 year, it will be close to 1.324. No, it should be 1.3.7 because it's closer to that value, 1 minus 1.2. And in case of 100, it will be close to 1.449. So we have to do the interpolation. So who can do the interpolation and tell me the values? Can you do the interpolation? And tell me what would be the KT for or skewness minus 1.21022.
Which T? 50 or 100?
For K50, I got 1.373379.
So you want 1 point?
37.
Yeah.
3379.
And now do it for K100.
1.44225.
How much?
1.44225.
1.44?
225.
325.
225. I think it.
1.44 225.
Yeah.
Okay. Okay, so let us see what other students they get. Okay, so I'm going to the my Excel sheet again. Okay, so we are trying to find out K50 and K100 by interpolation. So basically, when you do the interpolation, basically, first you write the your range of values. So for minus 1.2, your KT is 1.379. So that is your skew. And that is your KT. And for your skew of minus 1.3, you have 1.324. Okay. So when, so the interpolation problem is when our skew is minus 1.21022, what is our KT value? So that is our problem to find it. So very simple way of finding is that you find the difference of your KT between the two values. So this minus that divided by the difference between these two. And generally it's a good idea to ignore the sign, in my opinion. So 1 minus 0.3 minus 1.2. So you try to find out the absolute difference between these two by ignoring the sign. And then multiply that with the absolute difference between your skewness that we want to estimate, 1.21022 minus 1.2. So I'm using 1.2 as my reference. So that is the difference should be for the KT value in relation to my reference, that is 1.379, because I took that as the reference. So basically, my KT for that value would be this minus that. Which is, so that is our K50. So that agrees with the student that who noted that. So to find the K100, it will be very similar if we just change these values to what are our values for 100 year corresponding. It was 1.449. If I change this 1.449, and then this one was 1.324. Then the difference is this. So our K50, K100 would be?
For one, below one is 1.383. So for KT value for minus 1.3, the value is 1.383.
So for K100, we have to take from this minus that, if I am not wrong. Probably I have done something wrong, either right?
Yeah, your KT is wrong
The
for.
second KT value is 1.383.
Oh,
Yeah, should be
1.382. That's right. That's right. So I did not change it. 1.383. So then this is the difference here. And then for K100, we have to take the difference 1.44225. So is this interpolation clear to everyone? Very simple anyway.
so your K100 is wrong.
Sorry?
Your K50 value. Okay, never mind. Yeah, it changed. Never mind. It's okay.
So which one is wrong?
No, it's all right. You can go next question.
Of course, I can be wrong, but the calculation issue is there. Might be calculation mistake might be there. So
Sir,
now we can find out our Q100, is that right? We can find out our so we know our K50 and K100 now. So I am taking it a little bit higher up so that where I can see the equation there. So my I put my KT here. So I put it best special as values.
So before using the K50 value, you need to change the KT value for calculation.
That's right. So our K50 value we estimated before, which is 1.37.
37337.
337. That was our K50. And K100 was this, is that right?
Yeah, that's right.
So this is our KT values here. So now, once we know the KT value, then we can estimate our flow data. So first, let us compute log 10 of Q50, which is our equation. This is the equation M is this plus our standard deviation is this times our frequency factor is this for K50. So this is the log 10 Q50. So then Q50 would be it is log 10. So 10 to the power this value. So that is our Q50 estimation. And Q100, what is our Q100? We can estimate log 10 Q100 equals similarly as our mean M plus standard deviation times our K. So in this case, we took the K10, so that's fine. So that is on the log domain. So we can find out Q100 equals 10 to the power of, so we are doing anti-log. I think something is wrong here. Should not be like that. Log Q100 is the mean is this. I think something is wrong somewhere because let me do it again. So our mean, which is this, plus standard deviation of the data is this times our K100 is this. Okay, so that is there. We are doing something wrong somewhere. Let me see my previous solution. So this is question 4. So Q50 is all right. So we have not done Q100 here. I was expecting that Q100 value will be higher according to LP3 distribution. So let me see one thing. Let us see our table again. Maybe we are doing something wrong somehow.
Wait, sorry, it is higher though.
Now higher, but it's not that higher.
The Q100 is higher than Q50. So what's the problem with it?
1.2, 1.449. And 1.383, 1.37. Yeah, it's nothing wrong, but I was expecting a little bit like the LP3 distribution. Generally, Q50 and Q100 generally gives more difference, but it depends on the data. Anyway, so if your calculation is right, then that should be all. Okay, so that is the way that we do the LP3 distribution. So I think any question on this LP3 distribution? LP3 distribution is very important and generally comes in the exam. Okay, now the last question, I do it quickly. Compare the flood contrast for T equals 50 years and 100 years for Cypress Creek obtained in question 2, 3, and 4 by plotting in Excel. Comment on any differences. Which one do you think is the most accurate and why? So we have to plot this data and Q50 and Q100 on a graph, and we have to, so this is important how to make this graph. So you select this data. So we do a graph, insert, we scatter plot. I think we have selected the wrong thing here. Basically, we have to plot the flow and return period of the non-parametric method. Generally, we plot. So we plot in this way that we take this data here. And then we sort the data. So we have to select from the flow data, not from the total cell there. So go to insert and then so come to the data and then sort it with flow data with the largest to smallest. So the M value of the data is, this is 1. This is 2. So that is the rank of our data, and our return period or T value is, or the equation so that is the N plus 0.2. So our N is 40, is that right? How many years of data point we have here? M is the rank, which is my this cell minus, which we did before basically. And we copy it down. So this is our return period of the data. And I'll insert a column here. maybe another column. So basically, I have to plot so T in the x-axis and flow in the y-axis. So when you want to plot the data, this is very, very important for like the students, those who are working thesis. For example, who is doing honors students with me on flat frequency analysis or regional flat frequency analysis. Sanjeev, for example, it will be useful to them to this kind of plot to learn how to do it. So now we have to plot it. So we go to insert and go to scatter plot and do a plot of the data that we did before as well. So I'll go to the little bit further of the data where I'm not really, I have no other thing there. So this is the empirical data with the return period. So you have to create an axis title. So in the x-axis, it will be return period T here. And this axis title is observed data Q in meter cube per second. So that is the plot of the flat frequency curve, like the plot of the data of the flow data and all maximum flow data. Now we have to put our estimated value here from different quantile estimation procedure. So for T of 50 year and for 100 year, we have used three methods. Is that right? First, we have used normal distribution. Is that right? Normal distribution. And then what we have used? Non-parametric. Non-parametric, and then we have used LP3. Is that right? Okay, so what are the values we got according to normal distribution for 50-year return period? Anybody can recall? We've got 10152. And in non-parametric, depending on the what methods we have used, say I take 14307. And for LP3, how much we got? So students, you cannot hear me or you're not understanding what I'm doing?
Yes, I can hear, sir. We can hear.
So are we finding Q, like Q50?
So what are the Q50 values according to normal distribution? Is that right? 10,152, is that right? Can you go back to
for
your sheet?
LP3? For LP3, I think it's 10,284.
10,284, that's good. And what are the non-parametric for Q50 according to the latest equation that I gave? We did? I think nobody wrote it down, is that right? I can find it from there.
For normal distribution, it's 10,952 for Q100.
So how much we got Q100?
10,952.
10,952.
Yep.
And for LP3, how much we got?
10, 9, 2, 1.
10, 9, 2, 1. Okay. And for non-parametric, how much we got?
Let me check. For Q50, it's 14307.
14307. And for Q100?
25695.
25695.
Yep.
Okay, so these are the estimated quantiles we got. Now we want to superimpose this on this plot, which is the tricky part. And if you don't know it, then you have to, like, it's not easy to do it. I learned it from my supervisor. So select the data and say Control C. So I have copied the data and then I select the graph. And then I go to here, paste spatial. And then I go here, series names in first row, which is T, and the category X values in the first column. And if I say OK now, then you will find this distributional parameters, and we have to add a legend. So add a legend in the plot. And now we can see that the observed flow is this. And it's always a good idea to make the observed flow as hollow to format the data series. And so this is the flow data here. So I think that might be this one here, right? Fill and line, this one is effects. No line, gradient line. This one here. How did this one here? Anyway, okay, so basically what's happening here that we can see the flow data is this, and LP3 estimation is coming here. You see LP3 estimation is coming here, and flow data is going this way. And our normal distribution, where is our normal distribution gone? So normal distribution is not there.
These are like concurrent with the LP3.
Concurrent with the LP3, is that right?
Yeah, it's been covered.
Because they're very nearby, which is wrong. So that's why you see this data, LP3 and normal distribution, they are making very similar, which is generally unusual. But anyway, so this is the way that you prepare a flat frequency plot. And in most of the time, when we have the other return period, then we can join this as a line. So we can do format data series. And what is this? More things here. Vertical axis, vertical flow, series, normal distribution. So if we select the normal distribution here. So add data labels. Anyway, so basically we can add a line along these distributional lines. Once we have more quantized value there, we should draw a line among the that thing. So basically, this is the way we plot the data, and then we can compare with the observed data and make some. So you can see the non-parametric is going in that way. So in this case, probably non-parametric is better than the other two approaches.
Sir, excuse me, sir. So why you are thinking that is non-parametric is better? Like
because the observed data, we see the observed data is this blue color.
Yeah.
And you see the non-parametric is really trying to follow that observed data line.
Yes, so.
And your normal and your LP3 is quite big underestimation, you can say.
Yeah, downward.
Yeah.
Yeah.
This is happening due to a lot of smaller flood data in the series, because when you want to use LP3 distribution, then we have to censor the smallest flow, which is called the censoring of the data.
Okay, sir.
So if you use the flight software in the rainfall runoff, then it has the option to censor the or ignore the smallest flow data in fitting LP3 distribution.
And also, sir,
or we can use the EV distribution that we'll do. If you use the EV distribution, you will see that the EV estimation is much better than this normal and LP3.
Okay, sir.
Which is the extreme value distribution.
Sir, in your previous lecture, you showed us the formula to that criteria to cut the low flow and outliers.
You can use those kind of equations to censor the low flow, and that is possible. So you can ignore the smallest values in the data series because they are very small. They are not really flood, although they are annual maximum flow, but they are very small. So that's why when you feed the LP3 distribution or this kind of distribution, then we have to ignore those, not ignore, it's called censoring. You cannot ignore it completely, it's called censoring. And this censorship is really is available in the LP3, like the flight software.
Yes, sir.
So I think we don't have time to discuss it today.
Okay.
But you should really know it. But if you use GV distribution, you'll see that this kind of problem, you don't need the censoring because GV distribution is quite interesting and it is more powerful. And it is not much affected by the smaller flow in the data series. GV distribution is more powerful than this kind of distribution. So the most important thing is that there is no single distribution that is applicable equally good for all the stations. Because in this case, LP3 is not doing well, but in many cases, LP3 distribution will do very well.
Sir,
and in the same time, GV will do well for many stations, but for some stations, it will do very bad as well. So that's why I was still in for run of this time. They have said that we are not going to recommend any particular distribution. The user or the designer, they have to use their judgment and they have to compare different methods, and then they have to make a decision for the design flow. We don't want to say that use LP3 distribution or GV distribution or any other distribution.
Sir, can you just repeat how you add the second time below, like for the normal distribution?
Okay, so let us delete this first. So let us delete this point. Okay, so now we have only the observed data, okay?
Okay.
And now we have this table we have created, is that right?
Yes.
So I'm Control C means I am selecting it.
Yes.
And then I want to paste it on that graph. So I select the graph area and then go to the paste here and go to paste spatial.
Okay.
And then we select series names in first row and then category X values in the first column.
Okay.
And say okay.
Okay. Thank you, sir. Thank you.
Okay, so I think that's all for today. So I hope it's clear to all of you. So next week we have the exam and I will upload everything. I'll see what is not there in the news side. So I'll upload everything once this recording is come to me. It takes a few hours to come to me. And then once the recording is done, then I will immediately put everything on the website for you. And the exam will be based on lecture 1, 2, and 3. So that means that this lecture or this tutorial class will be included in the exam next week. Any question?
So for the normal distribution one, can we use the log Pearson graph using the zero
No,
skewness?
you cannot, because that is you cannot do. You know, for a normal distribution, you have to use the normal distribution table, because
Sure.
every distribution is different characteristics.
So it gives me the same value like when I use the like zero skewness coefficient, because if the ARI given to us is like the normal, like the usual ones, 50, 100, 20, then in the log Pearson type 3 distribution on chart, if you take the like the skewness coefficient as 0, because in normal distribution it's 0, then you can like, it saves a lot of time if you do that.
If the
Then you get-
skewness coefficient is 0, but your skewness is not 0.
So,
When skewness is 0, then it becomes log normal distribution.
so
Is that clear?
yeah, okay, thank you.
Any other question? I think that was a good question, that why we cannot use normal distribution. If your skewness becomes 0, then you can use normal distribution. But then in that case, you have converted the data into log. So that means you are using log normal distribution.
Yes, sir. But like, it actually gives you the same frequency factor, like 2.054 and 2.326.
I think that's why there has been some error somehow. I think there has been some error here, because it should not give the same frequency factor KT.
No, so your KT were different. You use a different KT because you use copy and pasted. That's why you get the same. But the K50, you used a different one.
No, sir, I said that
KT, like it should be K50.
Yeah, your K50 was different. You used put it the same as K100.
That's right. That's right. So that was the problem for the whole thing.
No, that wasn't a
So
problem.
what is our K100?
No, K100 is correct. K50
also you did it
So what is our
correctly.
K50?
So 1.37.
1.37337, is that right? 1.37337.
Oh, yes, sir. Yep.
337. So that is our K 50, is that right?
Yep.
So then our discharge values, where we calculate our discharge value here. No, we have used K50 1.37337 and K100 1.44225 in doing the calculation.
So what I actually said was, if you go to the LP3 chart, the corresponding values of the frequency factor for skewness 0 is the same as the ones we've got for the normal distribution question.
No, that is true. I have no problem with that. But our skewness is not 0.
So
that is not the issue here. Because your skewness is not 0. If skewness is 0, then you can use the normal distribution, that's fine.
And also I meant for the normal distribution question where you use the norm, descent norm, the Excel formulas.
Yes.
Instead of doing that, I'm talking about question 2 actually. For question 2, A and B. For Q100 and Q50, you use the Excel formulas to interpolate the frequency factors from the first chart for Z. But if you just, because it's normal distributed, it's literally says there, I think the data is normal distributed. Yeah, it says normal distributed, so which means the skewness is 0. So can we just go to the, because the ARI given to us is 150, which is actually present in the LP3 chart. So we could just plug in skewness as 0, and then the LP3 chart will actually give you the frequency factor for question 2 for 150
So you can,
as
instead
well.
of that, you can use the normal table as well.
So
because
normal
when
table,
your skewness is 0 for LP3, then it is at that point is normal.
yes, so that's what I'm saying. So like it saves a lot of time if you just use that chart.
No, that is not recommended. I will not tell that to you.
Okay.
With a different distribution, if you want to use normal, then you just use the normal distribution table.
Yep.
why you go to LP3, because if you want to use normal distribution, then if I say, okay, you can use LP3 distribution, then many questions will come, many confusion will arise.
Yeah, understood.
Okay, I think that's all for today. So see you next week. Thank you. Bye.
Thank you, sir.
Okay, thank you, sir.
Thank you.
Assalamualaikum, sir.
Thank you. So I'll stop recording.